Okay, very good afternoon, one and all. Today we can continue with the fifth chapter, module 1. Actually, we have started the module 1 in the earlier classes, where we have given the introduction for linear block codes. Okay, so in the today's class, let us go through the matrix description of linear block codes. Actually, we have started that concept and we are in the middle of that concept. We can complete that portion and we can continue with some of the problems regarding the error detection and error correction capabilities of linear block codes. Okay, so we all discussed about the importance of channel encoding techniques. So these are mainly used to detect and correct the error bit locations. Okay, and channel encoding techniques main thing is to detect and correct the errors, bit errors. And these implications of this error control coding, already I told you that this will increase the redundancy because we are adding check bits, R number of check bits to K number of message bits. This will increase the transmission bandwidth and it also adds a complexity in the decoding operation. Okay, so block codes are there are two types of channel encoding techniques. Already I told you, those are block codes and convolutional codes. Block codes are once again classified into linear block codes and cyclic codes. And already in this slide, already I told you that R0 is a channel data rate which is related to source data rate as R0 is equal to code rate multiplied by source data rate, where n by k is the code rate. Okay. And already I have given examples, various examples of linear block codes include the repetition code, parity check codes. All these we completed in the last class. Okay. And we have given the introduction for the linear systematic block codes. Okay. So what is the main thing? A linear block code is generally represented as n comma k code, where n represents the size of the code word, that is the number of bits present in the code word, and k represents the number of message bits, and n minus k will be the number of check bits, that is r number of check bits. Okay, so r number of check bits are added to k number of message bits in a systematic manner, which will generate a sequence of code words. Okay, and so this will form a sequence of code words, and each code word n. Okay, but please mute yourself. So here the term linear represents that the modulo 2 addition of any two code words results in the third code word present in the same code word sequence. So the modulo 2 addition here follows the XOR operation. So odd number of ones gives you, or you can say different inputs produces an output of 1 and the same input produces the output of 0. Okay. Now let us go through the matrix representation of linear block codes. So already I told you that linear block code is generally represented as n comma k. Okay, an n comma k linear block code gives you a hint that there are k number of message bits. There are k number of message bits, m1, m2 up to so on mk, and r number of check bits. Check bits are represented as C1, C2 up to so on CR. So these k number of message bits followed by r number of check bits produces an n-bit code word sequence, where n is equal to k plus r. N is equal to k plus r. It means that there are k number of message bits followed by r number of check bits. Okay, so therefore there are 2 power k number of distinct message sequences, because for example if k is 4, then you will have 2 power 4 number of message combinations that range from 0000 to 4 ones, and a 2 power n number of distinct code words. because the code word length is n, where n is equal to k plus r. So because n is equal to k plus r, we have n is a code word length. So how many distinct code word combinations are available? 2 power n. Okay. Now let us move in detail about the various steps for generation of code word. For example, let us represent capital X be the code word matrix of length 1 by n. So what is X? X is a code word matrix of length 1 by n. Which is equal to 1 by k plus r, where k represents the number of message bits and r represents the number of check bits. So X 1 by n is equal to m1, m2 up to so on mk, followed by k number of message bits, followed by r number of check bits, c1, c2 up to so on cr. So it is of size 1 by k plus r. It is of size 1 by k plus r, where k plus r represents the total number of bits present in the code word. So if you observe the columns, how many number of bits are there here in a code word? In a code word matrix or a code word sequence, here you can see that there are k number of message bits followed by r number of check bits, and a total of n bit code word will be generated. Okay, so code word matrix is of size 1 by n, and message matrix is of size 1 by k, and check bit matrix is of size 1 by r. Check bit matrix is of size 1 by r. So here you can say a code word of size matrix of size 1 by n can be obtained as a message matrix of size 1 by k followed by check bit matrix of size 1 by r. So total matrix size is 1 by k plus r. So k message bits followed by r check bits. So actually message bits are known to you. So message bits are known to you, and r check bits you have to calculate. So you have to calculate the r check bits in order to represent the code word. So code word, once you generate the code word, that will be sent via the channel. Instead of directly transmitting the message bits, code word sequence, or you can say a sequence of code words will be transmitted via the channel. Okay, so m message bits followed by k message bits followed by r check bits forms a code word. So a group of code words form a code word sequence. So that code word sequence will be sent via the channel. So m is a message vector matrix of size 1 by k, and c represents the check bit matrix size 1 by r. So check bits, already I told you, check bits are also called as redundant bits or parity bits. So what is a code word? It is of size 1 by n, consisting of k message bits followed by r check bits. Okay, so remember that so using message bits you can calculate check bits. So message followed by check bits gives you the code words. Okay, so this type of problems you need to solve. So please remember, code word is equal to, a code word can be constructed as k message bits followed by r check bits. Okay, so here you can observe a systematic structure where a code word is divided into two parts, and a k message bits followed by r check bits forms a code word of length n. Okay, so k rightmost bits of the code word are identical to corresponding message bits. So here you can see r is equal to n minus k. R is equal to n minus k. So how many check bits are there? N minus k, because n is equal to k plus r. So you can obtain r as n minus k. Okay. Now second matrix is, first matrix is code word matrix. So code word is a combination of message followed by check bits. K number of message bits followed by r check bits. So similarly, generator matrix. So actually we need to extract the check bits. That is important. So in order to generate the check bits, you need a help of one matrix called as a generator matrix. So generator matrix G, capital G of size k by n, where k is the number of message bits and n is a code word length. N is a code word length. This generator matrix is used for the generation of check bits. Okay, generation of R number of check bits. And this is used for, these check bits are generally used for error detection and error correction. Error detection and error correction. So x of size 1 by n is equal to x 1 by k plus r, because n is nothing but k plus r. So n bit code word is a combination of k message bits and r check bits. Okay, so I have written like this. So we can obtain the code word as m into g, where m is a message matrix multiplied by a generator matrix of size k by n. Now what is this generator matrix? So what is this generator matrix? So generator matrix k by n is represented as an identity matrix of size k by k followed by, here P represents the submatrix. Submatrix of size k by r. So here generator matrix is represented as an identity matrix of size k by k followed by submatrix of size k by r. Okay, so here if you see the overall matrix size, you can see that there are how many rows? K rows. And how many columns? In the first section, k columns are there, and in the second section, r columns are there. So k plus r columns are available in the overall generator matrix. So k plus r gives you n. So that's why here you can see that even if you see the two sections, identity matrix section and submatrix section, identity matrix section is of size k by k and submatrix size is of k by r. So you have k rows and k plus r columns. So that's why k rows by k plus r columns. K plus r column represents n columns. So where I k by k represents the identity matrix of size k by k and P refers the submatrix of size k by r. Okay. So what is the need of generator matrix? It is used for the generation of check bits. How many check bits? R number of check bits. And these check bits are used for error detection and error correction. These check bits are used for error detection and error correction. So generator matrix G of size k by n is equal to I k by k followed by P k by r. So please remember this. In the generator matrix, first you will get the identity matrix of size k by k followed by submatrix of size k by r. Please remember this format. So check bit matrix, what is a check bit matrix? 1 by r. It is of size 1 by r. It can be obtained by using the message vector matrix and submatrix pk by r. So check bit matrix of size 1 by r is equal to message matrix of size 1 by k multiplied by the submatrix. How can you obtain the submatrix? By using the generator matrix, you can obtain the submatrix. Take that submatrix and multiply with the message matrix. So m into p. So m into p, where p is a submatrix of size k by r, which can be obtained using the generator matrix. So m into p gives you the check bit matrix. So in order to generate the check bits, please multiply the message matrix with the submatrix. So let us see C1 by R consists of a single row and R columns. So C1, C2 up to so on CR, which is equal to message matrix is of size 1 by K, ante M1, M2 up to so on MK multiplied by this PK by R is a submatrix of size K by R. So it has K rows and R columns. k rows and r columns. Please remember C is equal to M into P, message matrix multiplied by P. For example, if you are given with 7 comma 4 code ichar ankondi, then M is 4. For example, take the first combination 0 0 0 0. So to get the check bit matrix for that 0 0 0 0 multiplied by the submatrix will be given in the question. So take that matrix and multiply. You can get the check bits. Those 4 message bits at a 0 0 0 0 followed by the 3 check bits obtained from this equation, because for a 7 comma 4 linear block code you will have 3 check bits at a C1 C2 C3 will be M1 M2 M3 M4 multiplied by the submatrix of size 4 by 3. Okay, this matrix will be given in the question itself. That is, a generator matrix will be given and you should identify the submatrix. Okay, because first you will have an identity matrix of size k by k followed by P matrix, submatrix of size k by r. Then you can obtain the check bits. So check bits ela calculate chestarma? Here first matrix is 1 by k and second matrix is k by r. So you will get total matrix size is 1 by r. So first you please multiply the first row of the message vector with the first column of the submatrix and M1 into P11 plus, see here, in order to add you need to make use of modulo 2 addition and XOR operation use cheyali. So M1 into P11 XOR M2 into P21 XOR up to so on Mk into Pk1. So that is C1. That is C1. So M11 into P11 XOR M2 into P21 XOR up to so on XOR Mk into Pk1. Similarly, C2 is M1 into P12 XOR M2 into P22 XOR up to so on Mk into Pk2. Similarly, CR, last one will be M1, M2, Mk up to so on Mk followed by that value multiplied by the last column. What is the last column? So M1 into P1R XOR M2 into P2R up to so on XOR Mk into Pkr. So like this you can attain the check bits. Now the 4 message bits. For example, check bits make 0 and 0 వచ్చాయి అనుకోండి. So 4 message bits ante 0 0 0 0 followed by 0 1 0 is the first code word. Like that you can calculate the code words of 16 message bit combinations. Okay, and fourth matrix that you should know is parity check bit matrix H R by N. So here this parity check bit matrix and generator matrix both are interchangeable. And knowing H you can generate, you can obtain generator matrix, and knowing the generator matrix you can attain the parity check bit matrix of size R by N. Please remember, generator matrix is of size k by N, where k is the number of message bits and N is a code word length. And parity check bit matrix is of size R by N, where R is the number of check bits and N is the code word length. So here you can write it is of size k by N. Okay. So generator matrix is of size k by N, where k represents the number of message bits, and parity check bit matrix H is of size R by N. Now, knowing one, you can calculate the other, and even vice versa will happen. So H is a parity check bit matrix which can also be obtained using the submatrix. So in the generator matrix you have seen generator matrix G is I k by k followed by P k by R. But in check bit matrix it is defined as P transpose, where P is a submatrix. So P transpose. So transpose అంటే ఎలా వస్తుంది? Interchanging the values of rows and columns, you can obtain the transpose. P transpose will be R by K because P will be K by R. So P transpose ఏంటవుతుంది? R by K followed by identity matrix of size R by R. So మీకు overall size ఏంటవుతుంది ఇప్పుడు? How many rows are there? R rows are there. How many columns are there? K columns in the first section and R columns in the second section. అంటే overall size ఏంటవుతుంది? R by N. So overall size will be R by N because you have R rows and K columns in the first section and R columns in the second section. అంటే overall columns ఏంటవుతాయి? R plus K అంటే N. So that's why I R by R represents the identity matrix of size R by R. And P refers the submatrix of size R by K. P refers the submatrix of size R by K. Now the transpose of submatrix P transpose can be obtained by interchanging the values of rows and columns. So transpose of P transpose, how can you obtain? P transpose of size K by R can be obtained by interchanging the values of rows and columns of submatrix. Okay, so like that finally we have 4 varieties of matrices you studied. First two are the message and check bit matrix. Message matrix is of size 1 by K and check bit matrix is of size 1 by R. Okay, message matrix is of size 1 by K and check bit matrix is of size 1 by R. And next one is code word. Code word is of size 1 by N, where N is A plus R. And a generator matrix is of size K by N, which is I K by K followed by P K by R. And C ఎలా calculate చేస్తారు? C is equal to M into P అంటే message matrix multiplied by submatrix of size K by R. And last matrix ఏంటమ్మా? Parity check bit matrix, that is of size R by N, which is P transpose followed by I R by R. Okay, please remember these 4 matrices because in the question you will be given with either generator matrix or parity check bit matrix. And in the question you will be given with either G or H, generator matrix or parity check bit matrix. Any one of these two will be given to you and you should know the value of P. Submatrix evaluate cheyali first, and after calculating the submatrix you can calculate the check bits C1, C2 up to so on CR. Then represent the message followed by check bits to get the code word. Okay. So we can discuss the problems in the today's class only, but before going to problems, let us know 2 more points. Once all the code words are calculated, how can you calculate code word? Message multiplied by submatrix. So message will differ based on the combination. For example, if there are 4 message bits, and total you will have 16 combinations. For all the 16 combinations, you need to evaluate the corresponding code words. Okay, so now once all the code words are calculated, minimum distance between the code vectors, let us consider it as dmin. Minimum distance between the code vectors, dmin, is taken as the smallest weight out of all code words other than 0. Okay, so you calculate all the code words and find out the minimum number of ones available in the code word. So that will be our minimum distance, that is dmin, other than 0. Okay, so once you calculate the dmin, please find out the number of error bits detected. Yes, as s plus 1 is less than or equal to dmin. How many number of error bits you can detect? Dmin minus 1. So s is less than or equal to dmin minus 1. And how many number of error bits are corrected? 2t plus 1 is less than or equal to dmin. So like that you can calculate either the number of error bits detected or corrected by using these two expressions. Now once you solve the problems, you will be more clear. Okay. So without solving the problems, if you see all these matrices, you don't know where you will use those matrices. Okay. Let us move into the problems. Okay, before going to Hamming code, let us move the two problems. Okay, so actually the question will be like this. మీకు exams లో ఈ మోడల్ లో వస్తాయమ్మా మీ questions. Problems you can go through the PDF which I have uploaded in the Microsoft Teams. Okay, so parity check bit matrix H R by N. So what is a parity check bit matrix? It is of size R by N, H R by N of a particular 7,4 linear block code is expressed as H3 by 7 is equal to some matrix is given to you. Now, any one of the student, please tell me what is this first matrix and what is this second matrix. Already I have shown you H R by N is, what is H matrix? Please observe the H matrix. Here you can see the matrix, that is the parity check bit matrix. Please observe this matrix and tell me what is the first matrix and second. So it is a combination of two matrices. One is P transpose and followed by identity matrix. So H matrix, if you see, you will have two sections. So sometimes the section partition will not be given to you in the examination. So మీరు ఐడెంటిఫై చేయాలి అది. ఓకే, సో హెచ్ మ్యాట్రిక్స్ అనగానే మీకు తెలియాల్సింది ఏంటంటే ఇట్ ఈస్ ఆఫ్ సైజ్ ఆర్ బై ఎన్, వేర్ ఆర్ ఇస్ ద నంబర్ ఆఫ్ చెక్ బిట్స్ అండ్ ఎన్ ఇస్ ద నంబర్ ఆఫ్ బిట్స్ ఇన్ ద కోడ్ వర్డ్. ఓకే, అంటే ఇప్పుడు 7,4 అన్నారు. సో వాట్ ఈస్ ద వాల్యూ ఆఫ్ ఆర్ హియర్? What is the value of R? 7 minus 4, that is 3. 7 minus 4 will be 3. And H3 by N is 7 here. So 3 by 7. H3 by 7 is given to you. And 3 rows are there and 7 columns are there. Out of 7 columns, messages have 4 columns and the remaining 3 columns are for the identity matrix. Okay. So first matrix will be P transpose matrix followed by identity matrix of size R by R at 3 by 3. Now you can be clear that this is a matrix P transpose. So meeku P transpose ichcharma. P transpose is of size R by K, because here you have 3 rows and 4 columns ante 3 by 4. So here P transpose is of size 3 by 4. Ante P matrix ent avutundi size. Any one of you please respond. Here H matrix is a parity check bit matrix. It is equal to P transpose followed by I R by R. P transpose is of size R by K. Can I know the matrix size of P? Any one of you please respond. Any one of the student please respond. First one is in the first section you will have P transpose matrix. This is of size R by K. Can I know the P matrix which can be used to get the generator matrix? P matrix size ent avutundamma? Any one of the student, please respond so that we can continue. So this is a P transpose matrix. Can I know the matrix size of submatrix P? C2, C2. C9, 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 lateral entry 19, D1, D1, H7, H7, H6, G5, G5, okay, I don't know whether you are speaking or not. Actually, I'm not. Okay. Okay, you can down your hand. Okay, thank you. You can down your hand. Okay, please listen. Here H matrix, it is a parity check bit matrix. It is a submatrix. Okay, P transpose of size R by K followed by identity matrix of size R by R. Here R is 3. Therefore, identity matrix is a 3 by 3 matrix. Now, so same model questions you will get in the examination. So please solve these problems. These are very, very important for your examination. Okay, so once the parity check bit matrix is given to you, you need to calculate the generator matrix. Sometimes generator matrix will be given to you and you should calculate the parity check bit matrix. Okay, so after calculating the generator matrix, second bit is calculate all the check bits and list all the code vectors. So check bits C can be obtained by taking the product of meshes vector and submatrix P. Okay, so once the generator matrix is known, you can calculate the submatrix P. Third bit is what is the minimum distance between the code vectors. And fourth bit is how many errors can be detected and how many errors can be corrected. Okay, so you can do this. I think you can see the same model problem in your PDF, in the PDF given to you. That is a handwritten material. See, you can see here, this is a model of question given to you. And once the submatrix parity check bit matrix is given to you, so knowing the parity check bit matrix, we can obtain the generator matrix. So generator matrix G is I k by k. So identity matrix of size k by k, followed by submatrix of size k by r. Okay, so here k is 4 and r is 3. So identity matrix is of size 4 by 4, I 4 by 4. So you can see identity matrix of size 4 by 4 here, and submatrix is of size 4 by 3. Okay, so generator matrix of size 4 by 7 is equal to identity matrix of size k by k ante 4 by 4, followed by already P transpose is known to you. So knowing the P transpose, what is the P transpose? In the first row you have 1110, second row you have 1101, and third row you have 1011. Now this is P transpose. How can you obtain P? So knowing the P transpose, interchange the rows and columns. So here first row becomes first column. First row is 1110. So here, so that's why first column will be 1110 and next column will be 1101 because second row is 1101 and third row is 1011. So that will become a column. So P transpose, applying the transpose to P transpose, you will get P. Okay, so interchange the rows and columns. And but the identity matrix for a generator matrix is 4 by 4 because it is k by k. Now, how many check bits are there? 3. Now you should calculate 3 check bits because given code is 7, 4. Given code is 7, 4 ichar. Ante how many number of check bits are there? 3. So 3 check bits can be obtained as C1, C2, C3 is equal to M into P and chepper. So M is message vector M1, M2, M3, M4 multiplied by submatrix that is P. P will be first column will be 1110, second column is 1101 and third column is 1011. Now message matrix multiplied by submatrix gives you the corresponding check bits. So how many check bits are there? 3 check bits. So C1, C2, C3 will be multiply the first row of message matrix with the first column of submatrix to obtain C1. So C1 is M1 XOR M2 XOR M3 XOR M4 into 0, that is 0. So andukani M1 XOR M2 XOR M3 M4 into 0 is 0. Next C2 is M1 XOR M2 M3 into 0 is 0 XOR M4 into 1, that is M4. So C2 is M1 XOR M2 XOR M4. So these are the equations. By using these equations, you can obtain the C1, C2, C3 for the message bits. So C3 is equal to M1 XOR M3 XOR M4. So the same I have mentioned here, because M2 into 0 will be 0. Now finally you obtain the equations for C1, C2, C3. So C1, C2, C3 you obtain the equations. So C1 is M1 XOR M2 XOR M3, because M4 into 0 is 0. Now for 4-bit message you have 16 combinations. Ante 0, 0, 0, 0, 0, 3, 4 zeros followed by check bits you have to calculate. Now C1 is M1 XOR M2 XOR M3, ante 0 XOR 0 XOR 0. That is 0 only. Next C2, M1 XOR M2 XOR M4, M1 M2 M4. So 0 XOR 0 XOR 0, that is once again 0. Next C3 is, because for even number of zeros, that is 0 or 2 or 4, then you will get the output as 0. For odd number of ones, you will get the XOR as 1, XOR output as 1. Next C3 is also 0. So for the first combination, you will get C1, C2, C3 as zeros only. Next for the second combination, 0, 0, 0, 1. So C1 is M1 XOR M2 XOR M3. Ante ee mooditki XOR తీసుకుంటే you will get 0. Next C2 is M1 M2 M4. M1 M2 M4. Ante 0 XOR 0 XOR 1. How much? It is 1, because it has odd number of ones. For odd number of ones, XOR output is 1, and even number of ones or 0 number of ones, output is 0. So C3 is M1 XOR M3 XOR M4. So it is 0 XOR 0 XOR 1, that is 1 only. Okay, so like that you can calculate, by using these 3 equations, you can calculate C1, C2, C3. Like how you can calculate? For odd number of ones, you will get the output as 1. For even number of ones, that may be 0, 2 or 4, you will get the output as 0. So accordingly, you can calculate all the check bits for the 16 message bit combinations, because it is a 7, 4. For example, if it is 7, 3, then you will have only 3 message bits. And then 8 combinations is sufficient. But here, because the K is 4, 4 message bits are there. So 16 combinations. For the 16 combinations, you can calculate the C1, C2, C3. Okay. So next, please evaluate the number of ones present in the code word. Okay. So let us see for the first combination, how many code words, how many number of ones are there? 0. For the second one, how many number of ones are there? 1, 2, 3. So 3. So for the third code word, so this is a code word. Each code word, first code word is all zeros. Next code word is M1, M2, M3, M4 followed by C1, C2, C3. So like this you have 16 combination. So for the second code word, how many number of ones are there? 3. For the third code word, 3. Fourth code word, 4. Fifth code word, 3. Sixth code word, 4. Seventh code word, 4. Please count the number of ones and post it here. Number of ones present in the code word. That is nothing but the weight. Okay. So accordingly, you will calculate all the number of ones present in each and every code word. That is 16 code words. Please write the corresponding weight or the number of ones. Now, what is the minimum distance? Already I told you in the PPT that, what I told you, the minimum distance is taken as the smallest weight out of all the code words other than 0. Minimum distance between the code vector dmin is the smallest weight out of all code words other than 0. So other than 0 here in this example, what is the minimum value? 3. So that's why d minimum is equal to 3. other than 0. So don't consider the 0 weight. The minimum weight is 3 here. Okay, so minimum weight is 3. So number of error bits detected can be obtained as, I told you the expression as s plus 1 is less than or equal to d min. So d min is 3. So s is less than or equal to 3 minus 1, that is 2. How many number of error bits can be detected? S is less than or equal to 2. Maximum number of error bits that you can detect for this 7,3 code is 2. Similarly, number of error bits corrected will be 2t plus 1 is less than or equal to d min. So t is less than or equal to 1. Okay, because d min is 3. So 3 minus 1 will be 2 divided by 2. So it will be 1. So t is less than or equal to 1. So like this you have to solve the corresponding problems, and this model of problems are very important for your examination. Okay, so please go through this model of problems. So ఇప్పుడు ఎలా డిస్కస్ చేసామైతే in the same manner, first using a parity check matrix, get the generator matrix. For example, if the generator matrix is given, get the H matrix and calculate all the check bits. List all the code vectors. Then calculate the minimum distance d min. Based on the d min, please calculate the number of error bits detected, that is s, because s plus 1 is less than or equal to d min. And using d min, once again calculate the number of error bits corrected. And 2t plus 1 is less than or equal to d min. So accordingly, you have to solve this model of problems, which is very important for your examination. Okay. So in the next class, we can continue with the syndrome decoding. So any doubts in the today's class? Okay, if you have no doubts,